Hey, this is Dr. Anna, and this is part 3 of the plate tectonics sequence. So I finished talking about the mid-oceanic ridge in the Atlantic Ocean and started to mention to you that the best and only example in the whole world when you can walk on the mid-oceanic ridge is in Iceland. It's really interesting place. On the next slide I have a really cool little video of a drone footage on Iceland. So this here is right the mid-oceanic ridge at Pingviller. You can see that it's being pulled apart right there. I'm probably not gonna play the whole movie, just showing to you how pretty and beautiful it is. Music is a little bit loud. See, people can actually walking in the ridge. Now we start talking about the convergent plate boundaries. They form above the down-welling part of the convection current in the mantle, and we have 3 kinds. The oceanic plate boundary, and when I say oceanic, that I mean oceanic lithosphere plate meets with oceanic lithosphere plate, and that forms the boundary. Then you got the oceanic lithosphere plate meeting with continental lithosphere plate, and the third one is when 2 continental plate is meeting with each other. So oceanic plate boundary, oceanic continental plate boundary, and continent plate boundary. So let's start with the oceanic plate boundary, and I have a little sketch what I made here before, so you can see that I drew the oceanic plate right here, and that's the one which is going down. Normally always the one which is colder and older will go down. So that's one oceanic plate. This is the other one right here, oceanic plate. This is the sea level. I think I put down ocean right there, so it's the sea level basically. I'm gonna put sea level right there. Now we already kind of listen to this, like as it goes down the rigid oceanic plate, it starts warming up as it goes down into the much more hot area. As it heats up, it starts melting, and remember when it molten, it's less dense, so it starts going up, easily going through the oceanic plate, and will make volcanoes. So this is a volcano right here, and we call that island arc. Okay, island arc or volcanic arc. Island arc or volcanic arc. The deepest area right before is the trench. We have here the back arc basin, but it's not that important in this class. So what I really want you here to know that this is the oceanic plate. That's the other oceanic plate. The colder, older is going down, and because it starts melting, melt is always less dense. It comes up, goes through the oceanic plate, makes the volcanic or island arc. And you have to know that that's the trench and that's the island arc. Now, this process is called subduction. That's really important that you know that. The best example for oceanic plate boundary is Japan. Here you can see the animation of the subduction process. Oceanic plate going down, forming the volcanic arc. This here showing you the Google Earth view of the Japan area. This here is the Pacific Ocean. This is the trench. This is the island arc. Japan is right here, island or volcanic arc, remember? And wherever you see the islands, that is the plate which is not going down. So the colder, older oceanic plate is the Pacific Ocean. So that's the one which is going down. And right there is the trench, which is forming like as it goes down right there. See? It's going down and the trench is right there. So you can see the Pacific Ocean is going under the Pacific Ocean plate. So not the ocean, but the Pacific plate is going under, forming the trench. And as it melts, will make the volcanic or island arc. It's very logical, isn't it? So the next one is the oceanic continental plate boundary. So remember, what did we say about the density of the continental plate? It's 2.7 gram per cubic centimeter. It's 2.7 gram per cubic centimeter. You really need to know it for the exam. And the oceanic plate is about 3.3 gram per cubic centimeter. The mantle is about the same. It can easily be pushed down into the astrosphere. And as I already draw it before, this here is the oceanic plate. So the sea level is up here, and this here is the continental plate. And again, as it goes down along the subduction zone, so this here is the subduction, it gets warmer, hotter, starts melting. When it's melting, it's less dense, so it starts going up and goes through the continent, making the volcanic arc. So now the volcanic arc is always going to be on the continent. And continental plate can never go down, ever. So make sure that you understand the oceanic plate is more dense. And this is just a 3D picture of the same thing. So you can see the oceanic plate is going down, not the continental. Here is the trench. And as the plate goes down, it will warm, melt. The volcanic arc is going to form on the continent. It's always going to be. And this is the Google Earth example. The best example for this kind of plate boundary is the Andes. And here you can see that the Pacific plate is the one which is here, and that's what goes down. Here is the trench, and these are the volcanoes right here. And the last type of plate boundary, the last type of convergent plate boundary is when a continental plate meets a other continental plate. Remember, we just said that the density of the continents are 2.7 gram per cubic centimeter. So when they meet, and normally when two continental plate is going to meet, there was an ocean before, so it went through a subduction, an oceanic continental plate boundary, and then the other side of the continent gets there, and then finally the two continent meets. I will have a low animational video just after this. So the two continent meets, they both are very light, they cannot go down, so what's going to happen? Yeah, you're right, they will have to be moving upwards, and this is what we call collision. This is what we call collision. And usually this is how the really high mountains are forming. In a lot of the cases in the high mountains, if the plate was before an oceanic plate or a shallow continental shelf, then as they go up against each other, the fossils are going up, of course, from the shallow marine environment. And you can go up to the top of the Mount Everest and we'll find seashells on top, like 8,000 meter high, you're gonna see seashells. Yeah, and here is the animation. And I'm gonna start it right here. This is India and Asia. And you can see how the mountains starting to form. Continental crust can never go down. This down here is the old oceanic crust. And that is melting back into the mantle or the astrosphere. And here is the Google Earth view of the same area. So this is India and Asia. And this is the Himalayas right here. So a typical continental plate boundary when they collide with each other is the Himalaya between India and Asia. The third kind of plate boundary is transform plate boundary. This plate boundary is usually located along the mid-oceanic ridges, right? That's the boundary, and we call it, it happens along a transform fault. And there is an explanation video I found.
Set by short transform boundary segments. Plates move in opposite directions along these segments, making them a source of shallow earthquakes in the ocean basins.
These offsets are essential for allowing the rigid tectonic plates to move over a spherical Earth. By way of analogy, imagine trying to wrap a ball with a rectangular sheet of paper. We have to make many small cuts in the paper to fit it to the ball's rounded surface.
Earth's plates are rigid slabs of rock that have to make small adjustments to slide at different rates and different directions over the planet's surface. These small transform segments represent some of these adjustments.
Example right here. As you can see, the mid-oceanic ridge, remember on the spherical Earth, has to adjust, so that's why the transform faults are forming, the transform plate boundaries, and then just a little bit over, the mid-oceanic ridges continues. So that's a good example. It's the Wonderfuca place, and that's where the Pacific Ocean is going under North America, and it happens very close to this. So that's the Wonderfuca place, and that's the trench, like as it goes underneath of North America. Now, as the mid-oceanic ridge is going under North America, one of the transform plate boundaries run onto the continent. So here we are, that's the San Andreas Fault, which is a typical transform plate boundary. So you can see the San Andreas Fault is actually making Baja California and Los Angeles being on the Pacific plate. So Los Angeles is on the Pacific plate, but as you can see, San Francisco is on the North American plate. So interestingly, the Pacific plate, Oceanic, the Pacific lithosphere plate is moving to the north, where the North American plate is going to southeast, northwest, and southeast. So the Pacific plate is moving northwest, and the North American plate is moving southeast. So after a while, San Francisco is getting closer to Los Angeles. So there are these funky stories that one day Los Angeles is going to fall into the ocean. As you can see, it's not true, but every earthquake will bring them toward each other a little bit. So if you want to be living in San Francisco, it's a good idea to buy some property around Santa Monica, right here, and just wait. And then about 5 million years from now, you're going to be right in San Francisco, which is kind of interesting. So this is the San Andreas Fault itself. And it's running in California, going onto the continent at San Francisco, and goes all the way to the Gulf of California. And the last thing we have to talk about is the hotspot volcanoes. One of the best examples for hotspot volcano is Hawaii. It's extremely interesting. So there is an area in the mantle which has a little bit more radioactive elements by decaying, producing a little bit more heat than other places. So that's what we call hotspot. And you have to imagine that the crust is moving over the hotspot. That will result in a chain of volcano, where the one above the hotspot is always producing volcanoes. As it moves over the hotspot, the volcanoes which were before over the hotspot, right above the hotspot, are now not active volcanoes. There is always one active volcano each time, the one which is right above the hotspot. So if you look at the Hawaii volcanic chain, see, Hawaii, the big island, is very active right now. You hear it all the time. Maui is already not dormant, it's a dead volcano because it's already moved away from the hotspot. And Oahu and Kauai is all dead volcanoes. So they are not active anymore because they moved away from the hotspot, which is right here. So these guys are older and dead. They will never erupt again. So if you don't want to be around the volcano and you want to move to Hawaii, it's the best if you move the other places. Of course, Maui just had the fire, which is not so good. But that's because remember that hurricane came by, and that's the hurricane strength winds started the fire really quickly. Now there is a very interesting there is a hotspot which was on the Pacific plate, and that hotspot moved underneath of North America, and it started to go under North America right here where the Columbia River Gorge is coming in. And there was a lot of lava forming because of the hotspot went under the continents, and right now it's underneath of Yellowstone. But you can kind of see that there are places before where it made like big calderas and craters. This one here is 12.5 million years old, 10.3 million, 6.5 million years old, and the Yellowstone caldera is active it had some big volcanic events around 2 million years ago and 600,000 years ago. So the hotspot track is moving toward the east, and it's because the plate is going, the Pacific plate with the hotspot on it is moving underneath of North America and moving under, so it's going further and further from the beach. This shows you the Yellowstone caldera. We will talk a whole lot about it because this is one of the biggest supervolcano on the whole wide world. And it's in America. Isn't that cool? I don't think so. Because if Yellowstone would erupt again, that would be really, really devastating and a big volcanic winter, which would probably be about 10 years old. If Yellowstone produced another eruption as big as the one 2.2 million years ago, it would be really, really bad. And you can see the magma chamber right here is about 5 miles below the surface. So it's very close to the surface. Very, very close. And so it can erupt any time. We never know when that would be happening. One more time, I'm showing you the transform plate boundaries. So this here is just showing you the whole Earth with the plate boundaries. And this shows the lithospheric plates and the type of plate boundaries. The red are going to be the divergent, the blue is the convergent, and the transforms are the yellows. So you can see how lucky we are in North America, because if you just travel to the west, like down here is the Gulf of California, which is typical divergent. Then you are on the San Andreas, which is transform. And then you are in the convergent plate boundary. Oregon and Washington are typical oceanic continental plate boundaries. So what a cool place. And the very last picture is really interesting. This shows you the age of the oceanic crust. And the dark blue is about 180 million, see right there, 180. And this is here, the really dark red is the basically today. So you can see this is the Atlantic Ocean with oceanic ridge in the Atlantic Ocean going right here. Here is Iceland. You can see that the Atlantic Ocean is very beautiful, very symmetrical. The oldest crust is right here where we are, and that's when the Atlantic Ocean started to open up, and it's about 180 million. That's about the oldest oceanic crust in the world. So you can see that the Atlantic Ocean is a very young opening ocean, very active, no subduction, only divergence along the mid-oceanic ridges. You can also see the transform plate boundaries all along, which is the adjustment to Earth being sphere. Now, on the other hand, if you look at the Pacific Ocean, you can see a little bit of old crust right here, but you can see that the mid-oceanic ridge is not in the middle anymore, and it's not symmetrical at all. Basically, the mid-oceanic ridge is going right against North America right here. That just means that half of this ocean is missing. It went under and subducted back into the atmosphere, into the mantle, basically. And what is interesting that as the mid-oceanic ridge going under North America, you're gonna have divergence going on to North America. You will see a lot of features which is very characteristic, like the Coachella Valley, which is Palm Spring, that area of California, the Salton Sea. Then you go up to Death Valley, and then you go up to Utah and look at Canyonland. That's all result of this divergence. So it's amazingly interesting. The United States, the western part of the United States plate tectonically is extremely interesting. You have the divergent, transform, convergent plate boundary. You have the hotspot in Yellowstone. So if you ever travel that area, you won't be able to see anything but geology, and you will always think of me because I am the one who pointing this all out to you. I hope you enjoyed plate tectonics, and I will see you in the next module.